Hello students, we will begin with the syllabus, that is module 1. So we have classical mechanics PHCT 112, and in the module 1 what all we have? This is analytical dynamics, which is Lagrangian and Hamiltonian dynamics, canonical transformation and Poisson's bracket. This all is module 1. So module 1 actually has 2 credits. Module 2 and 3 are 1 each. So this itself, when you finish this is 50% of the syllabus is covered in the module 1. So module 1 begins with this, but I can't think of beginning with this topic. I'll begin with the introduction of, like, moment you say you have to study mechanics. So what is mechanics basically? Mechanics is a branch of physics that everybody knows, which deals with the physical objects in motion and at rest under the influence of, we can say, the external and the internal interaction. Now when you say physical objects in motion, okay, means what? For example, suppose I have a rigid support to which I attach a thread, and over here I have a bob whose mass is m. Okay, so this bob will be here until and unless somebody picks it up, take it to one side and release it. Okay, suppose I will take it at this angle, correct? So what will happen? This is my angle theta, this is the length L of the pendulum. Fine. So until and unless you take it over here and release, then it will cross this, come to this side, again come over here, and this is the way we will be able to measure the oscillations of this simple pendulum. Fine. So this you know very well. So once you know this, okay, this is, I should say, one example of observing the physical objects in motion. Under. So in this case, what you want to understand first, that in this case we'll have to talk about how the oscillations takes place, the like how you try and find out the equation for energy and so on. Okay, so that I'll come to it again little later. But another example I can give you. Suppose you have this support, okay, and here I have what is called as a spring attached to the rigid support, and to one end I have put a block whose mass is m. Fine. Now this block, suppose I keep it as it is, nothing is going to happen until unless I either compress it or stretch it. This is rest position. Okay, so there are 3 positions where the block can be. Either it will be in the compressed position, or the normal rest position, or the stretch position. Fine. Understood? So depending on, either it will be over here, okay, or here or further. So this is the displacement what we are going to observe. So moment I talk about the word displacement and so on, you need to understand the word F. So what is F? Is the force. What is this F proportional to? F proportional to X. What is X? Displacement. Fine. So now moment the word F has come into the picture, okay, you can use the word, yes, mechanics developed by the scientist on the basis of observations on the motion of the material particles. So in which who was the first scientist who worked on this? Newton was the first scientist who had written his rules. Okay, so Newton, what all he did? He announced his laws of motion. Everybody is studying these laws of motion from your school days. Okay, there are 3 basic laws of motion which everybody must have by hearted, starting from the law of inertia, then second for the momentum, okay, and so on. So the mechanics basically based on Newton's laws of motion and alternatively developed by what is called as Lagrange and Hamilton Okay, even these two words you must have listened in TYBSc. So Lagrange and Hamilton and few others, okay, is basically called as classical mechanics. Because you should know why this is named classical mechanics, because here we are going to observe the motion of the system or physical objects in motion, of whom simple examples like this, and everywhere you will be able to need to use these Newton's laws and little more advancement by this scientists Lagrange and Hamilton and few others. So the mechanics developed by them will be basically called as classical mechanics. Understood? So when this mechanics deals with Newton's laws, okay, and their consequences, okay, it is also called as classical mechanics, or it is also called as Newtonian mechanics. I don't know, have you heard this word ever? But because of Newton's laws of motion are valid for many systems, that's the reason it is also called as Newtonian mechanics. Now in this, what I use the word? I use the word force. Okay, what is F? F, you say F is equal to ma. Okay, so force, acceleration, momentum, etc. all are vectors. So even this is also called as vectorial mechanics. Okay, but instead of these two names, they have decided upon classical mechanics. So at least now at this PG level, you should know the reason for your subject. Understood? Now the alternative or the superior mechanics, superior schemes in classical mechanics developed by, there are few more scientists named as D. Lambert, even you must have heard this name, then Lagrange, Hamiltonian and few other, constitute analytical mechanics. Analytical mechanics. In this, what are the quantities involved? Quantities involved basically are scalars. Okay, for example, what? Energy. Okay, energy and dynamical relations are obtained by differentiation. If you do not get directly, differentiate it and you will get it. Okay, so therefore, correct, the name, so along with Newton and every word and everyone like Newtonian, vectorial, but then you will say, then what about few scalars involved in that? That's the reason some advancement took place and everything is covered in our classical mechanics. Not only Newton's laws of motion, not only vectors, scalars also are involved. That's the reason everything is covered under classical mechanics. Okay. Now classical mechanics is not completely, or we should say adequate. It is inadequate. For what? Inadequate to describe the behavior of particles of microscopic size. What do you mean by microscopic size? So here we can say this is the limitation of classical mechanics. Microscopic size. The example I can say is electrons. Okay, electrons in an atom, nuclear particles, etc. We will not be able to observe the motion of electrons in an atom by classical mechanics. Okay, so what we can say over here, classical mechanics will fail and you need to approach some different view that will come under what is called as quantum mechanics. So limitation for classical mechanics has come to study microscopic size, for example electrons in atoms or nuclear particles, where quantum mechanics will come into the picture and quantum mechanics will help to observe or to study the motion of those particles. Fine. So in classical mechanics, it is useful basically to study motion of relatively massive particle, not very huge, but relatively massive particle, and also the slow moving objects. Now what do you mean by slow over here? Over here, I do not want this simple pendulum to have a large oscillations. This theta should not be very large. I don't want this over here. I want a very small amplitude by which the oscillations what are we going to observe will be in control and will not ever think of going out of control. That is also very, very important. So classical mechanics is useful to study motion of relatively massive, not too much massive, and also the slow moving particles. Okay, now we'll just define few things. First is frame of reference. So when do you use this word? What is the significance of this? That I just want to tell you. So over here, what we say to describe the motion of a particle in space. Okay, moment I say space means x, y, z coordinates along with the time. So one needs to know its position at different instants of time. At t1, where it was located, at t2, t3, and so on. So this needs the choice of reference body or coordinate system. Suppose I just draw the xyz over here. This is the origin, this is my z axis, x and y, and here I have a clock. Fine. Suppose this is my clock. So this will take care of the time. This is point P, and suppose I join from point O to P, this will be radius. So P coordinates will be x, y, z and t. Fine. So if you imagine a coordinate system attached to a rigid body and we describe the position at any particle relative to it, then such coordinate system is called as the frame of reference. So what is this figure is showing? This figure shows a simplest frame of reference, okay, is a Cartesian coordinate system. In this case, what you see, the position of a particle at any point, okay, of its path is basically given by r. So what we say, r is basically given by xi plus yj plus zk. Okay, xi, ij, k are the unit vectors along x, y and z direction respectively, that everybody knows. So when position r and time t are recorded together, okay, represented by x, y, z, t, and reference system used for this purpose is called the space time reference system. Okay, so this is just a one definition I mentioned. Obviously, as I mentioned earlier, you should know the Newton's law very well. Okay, without that classical is difficult. Okay, then we'll define one more thing which is called as inertial frame. This definition you can revise on your own also, but I just thought I should take this before going to the main point. Okay, suppose here I try and expect to draw the x, y, z also. So over here, this is my z axis, x axis and y axis. This is my in frame S, suppose I say. I want to define inertial frame. Okay, so this is S. Now I take a point O dash somewhere over here and draw. This is O, obviously. This is now x dash, z dash, and I join O to O dash. Okay, this is O dash. Now I take point P in the frame S dash. Fine. This is y, so this will be y dash. This is x, this is x dash, this is z, this is z dash. Okay, and this is vt. Fine, because I am showing v in this direction. Okay, now what I want to say, I want to say that suppose I join the particle P from O dash like this, I'll call that as R dash, and suppose I join this point over here, okay, this will be my R. Done. So what I want to say in this case now, that Newton's laws of motion are valid in reference system. Now we know reference system is what? Known as the inertial frames. So what is inertial frame? An inertial frame is the one in which the laws of inertia holds true, which means the first law of motion holds true. Now if a particle subject to no external force is found to move in a straight line, okay, with constant velocity, then the coordinate system used for this purpose is basically called as inertial frame. So in an inertial frame, a body not expressing any force, okay, there is no force, appears unaccelerated, that is F is 0, unaccelerated means even A is 0, okay. So as Newton's second law says what? F is equal to ma, suppose, is equal to 0, and what is acceleration? It is g2r by dt square, even that is 0 because we say A is 0. So all those frames which are moving with constant velocity relative to an inertial frame are all inertial. That's what we have understood over here. Okay. Now we'll see few basic concepts before I go to the main topic. Now in the basic concepts, what I need to define first, I need to define the topic itself is basic concepts, in which the first one will be coordinate system. Coordinate system. Now in this, okay, I'll try and draw a normal two-dimensional only x and y, okay. Take obviously point P, then coordinates will be x, y, join from origin to point P, that will be r, this will be theta, fine, and you take a perpendicular and over here, so this side will be x, this side will be y, from here to here and here to here, fine. So now everybody knows that there are two coordinate systems, one is xy, that is normal coordinate system, and a polar coordinate system, okay. So now if I know xy are the coordinates for the point P, and it is joined to the origin by distance r, and it has got the angle theta. So everybody has studied that x is equal to r cos theta and y is equal to r sin theta. Fine. Suppose I try and square both of them and add. Okay, even that you must be knowing, but my duty to explain it to you again. So I'll say if at all I square them, you get x square is equal to r square cos square theta, and you get y square is equal to r square sin square theta. Suppose I try and add them, so what I get? X square plus y square is equal to r square, because cos square plus sin square is 1. Fine. So what does this gives me? This gives me r is equal to under root x square plus y square, and obviously if at all I take the ratio, okay, if at all I say y by x, what is y? R sin theta, and what is x? R cos theta. Okay, cancel r, you get tan theta. So what is my value of theta? This gives me tan inverse y by x. So I know the value of r, I know the value of theta very well. So once I know x and y, I can very well take the polar coordinate system to be in case of r and theta. Fine. So if this is only for a two-dimensional, suppose I say I use a spherical system, spherical coordinate system, okay. So in that case, instead of r and theta, you might have more variables also, like r is a function of r, theta, phi and t also, okay. That's the reason. Actually, you do have, in general, r is basically a function of q1, q2, q3, qn and t. These are my generalized coordinate, okay. I'll define that in a few minutes. This is the first basic concepts I should know. Second one is the degrees of freedom. Even this word you have studied in your TYBSc syllabus, but my duty is to revise for you in this case. Now, degrees of freedom is a very important concept. Okay, so what you want here, you want to express or explain the minimum number of independent variables or coordinates. We'll say coordinates basically. So minimum number of independent coordinates required to specify the position of dynamical system consisting of one or more particles is called degrees of freedom. Okay, suppose I want to take the example now over here. Suppose I want to study motion of a particle freely in space. Okay, so what all it needs? Particle in space. If you say particle in space means 3 coordinates x, y, z. Okay, so degrees of freedom also will be 3. Fine. Now I say I have 2 particles moving freely in space. The degrees of freedom will become 3 into 2, which is 6. If there are n particles, what will I say? N particles moving freely in space. So therefore 3n is the total number of degrees of freedom. Clear? So it is as simple as possible that the minimum number of independent coordinates required to specify the position of dynamical system is basically my coordinates or degrees of freedom. Okay. Next definition which we need to study is constraints. Even this word you must have been used in your TYBS. Now constraint basically is restriction. Okay. So what is definition of this? The motion of a particle or system is restricted by one or more conditions. Okay, so the limitation on the motion of a system are called as constraints, and the motion will be constraint motion. Okay, means what? Suppose you have this is origin, this is the circle, and suppose I draw like this. Okay, and I see that the particle is moving over here. This is a ridge part. Particle is expected to move only on this part, not inside, not outside. Okay, suppose the particle is moving over here. What we can see, that the coordinates required will be, this is r, okay, and depending on the position, theta. Now you will say that the particle is not allowed to move either inside or outside, means the constraint is that the particle has to move only along this. Take an example of live example, the train. Okay, the train has to move on the track, fixed distance. It can't think of going here or here. The train will get derailed. You must have heard this word. I must have seen the accidents also. So there is a condition that train cannot think of losing the track and come down on the ground. Okay, so to avoid that, take an example of a carom. Everybody must have played carom in their childhood. So on the board, everywhere in the corner you have these holes. Okay, so when you take a striker in your hand and strike it, either the coin will go here or here or here or here or somewhere over here. But the restriction is that it should not cross the board and come down over here on the ground. Understood? So this is the way the condition imposed on the particle or the coins, like you usually arrange the carom board like this and then strike it. Okay, so which means the condition over here that it should not fall down, it should be somewhere over here on the carom board itself. Fine. So the limitation on the motion of a system will be called as constraint, and the motion will be called as the constraint motion. Okay, now we'll take only one example, one definition, generalized coordinate. Generalized coordinate. This is now why you need to study this, that I'll tell you also. So in this, minimum number of coordinates needed to describe the motion of the system. Okay, for example, like I explained you earlier, that the particle is constant to move on circumference of a circle. This example itself. Okay, so basically you have two coordinates required, r and theta, but as r is fixed, only one coordinate, that is theta. So this is the what I am saying, minimum number. Instead of moving along the circumference of a circle, there will be two coordinates, r and theta, but as r is fixed, only theta is sufficient for me to describe the position of a particle. Okay, so this is the way I can say that the generalized coordinate in this fashion, r is constant, so only theta is sufficient to describe the position of the particle. Now you say the generalized coordinate for a system of n particles. Suppose I have a system consisting of n particles. Okay, suppose I have n particles. So what I said earlier, the degrees of freedom, it is 3n. Fine. So in this case, what will I say? The generalized coordinates for a system of n particles will be 3n, but constrained by m equation, so minus m. Okay, depending on what are the constraint, subtract from that and you will get, like here I had two coordinates but minus 1 because r is constant, so only one generalized coordinate. So here n particles, constrained by m equations, 3n minus m. So this is the way we will try and study further our classical mechanics topic. So in my next video lecture, I'll take now for this topic what they say, Lagrangian and Hamiltonian equations of motion. Okay, so to revise this, I'll try and take 2 to 3 examples where we'll try to find out the motion. To get the Lagrangian, you need kinetic energy, you need potential energy, you need the equation, and you get a final value. So I'll take at least 2 to 3 examples to get this concept clear before going to the variational principle. Fine. So feel free to ask if at all you have any doubt in whatever we have finished. But every word, whatever I said, is very, very important. So watch this video depending on your how much you can grasp. Okay. Try to make your notes if you want on your own, or if you want to make these notes, you can reduce the speed if you want and then make it. Okay, because everything is depending. The next topic what else depend will be something we might require from this also. So I'll assume that you are understanding it. That's the reason it will be very helpful if at all you try and make the notes on your own. Okay, go through it. Thank you very much.